In this video, we're going to examine the pigeonhole principle. The principle says that when we have M items or pigeons and we're trying to place them into N containers or pigeonholes, when we've got more pigeons than pigeonholes, then at least one pigeonhole will contain more than one item. So as an example, let's consider that we have 5 items and we have 4 containers. So here below are 2 examples of how we could place these 5 items into the 4 containers. And as we can see, at least one of these containers has 2 items in it. Because we have one extra item than containers, one of them has to contain 2. So if we have n plus 1 items and only n containers, one container will contain 2 items. So let's have a look at a couple of examples just to thrash this out a bit more. In a group of apartments, there are 10 letterboxes. What is the least number of letters required to guarantee that one letterbox will have at least 2 pieces of mail or letters? So if we think about this, we have M that we don't know, but N as 10 letterboxes. Well, we're going to have 10 letters so that one goes into each letterbox and an extra one to ensure that one letterbox has 2 pieces of mail or 2 letters. So we need 11 letters. So there we can see that M is N plus 1 to have one letterbox with at least 2. In example 2, if you have 7 balls to be placed into 4 boxes, then at least one box will contain 2 or more balls. So here's an example of a placement that we've put 4 balls in and placed them one in each box, and then the next 3 balls have been placed as follows. This means that one box contains 2 or more balls, at least one box. In fact, in our example, we've got 3. So if we have 13 balls and 4 boxes, at least one box will contain how many or more items? So let's consider our 4 boxes. So we can place a ball in each, and we can keep going as an option of placement. And we've used now 12 of the balls. So we've got one more ball to place, which means at least one of the boxes will contain 4 or more items. So visually we can represent that as an example. We could also do it using some mathematics, thinking if we've got 13 balls and we have to share them into 4 boxes, we get 3.25. Now if we consider taking the integer value of 13 over 4, then we end up with 3, which means that one of the containers will have at most 3, and then the other containers will have the integer plus 1. So we have at least one container with at least 4. Let's have a look at example number 3. 7 pairs of shoes, which means we've got 14 shoes in total, have been jumbled into one large box. So we want to consider the minimum number of shoes that we have to choose from the large box to ensure or guarantee, we have at least one matching pair. So think about pulling out one shoe at a time. So we would actually have to pull out 7 shoes. And 7 shoes, we could find that we have no pairs because they could be the 7 shoes from the different 7 pairs. So we need to have actually one more shoe to ensure that we would have one matching pair. So the minimum number of shoes to be chosen to ensure at least 3 matching pairs, we could go through and choose the 7 shoes, but then we need to choose another 3 to ensure that they all match to one of the 7 that was chosen in the first group of 7 shoes. So we'd actually need 10 shoes to be chosen. We can think of this in another way. 6 shoes are chosen. What's the maximum number of matching pairs possible? So if we think about those 6 shoes, if they all had some form of pair that matched, we could get a maximum of 3 matching pairs. That's like a best case scenario. Let's consider our final example. 15 balls are distributed amongst 4 boxes. There must be at least one box with no more than P balls and at least one box with at least Q balls. Find P and Q. So if we think about the fact that we've got 15 items and 4 boxes. So if we look at 15 divided by 4, we get 3.75. So if we can compare the integer value of 15 over 4, or m over n, we end up with 3. So if we consider our 4 boxes, we're going to place 3 into each box, and that will give us our 12. So we have to place at least one more into at least 3 boxes or into another one to say that we have at least 4. And this is the idea of having the integer value plus 1 to show us that we could have at least 4 in at least one of the boxes, but no more than 3 in the other. So here we could say that P is worth 3 because that's one box with no more than P balls, and Q is at least one box with 4 balls. We could generalize this to say the lower value we get when we take the integer of the items divided by the number of containers or boxes can tell us what will be in the maximum in one container being at most that value, and the upper value would be the integer between the number of items in the container plus 1. And this will be the minimum of one container with at least this many. So now it's your turn to have a look at the following questions on your sheet. Question 1, question 2, and question 3. So please pause the video and then we will have a look at the solutions to these that we can debrief in class. And here are the solutions to the 3 questions above.